So to recap to what we have done so far, we went and developed the Reynolds transport theorem, which relates the change in the extensive property of a system, denoted by capital B, over time, to the change of the intensive property corresponding to that extensive property, which is denoted by little b, in a control volume, plus the rate at which that property flows across the control surface, which is given by this expression here, which is the density times the intensive variable times the velocity dotted with n hat integrated over the control surface, where the v dotted with n gives us the amount of flow, the velocity over that's perpendicular to the control surface. That is the velocity component that is actually leaving the control surface. Now, we briefly talked about conservation of mass, and we're going to develop that a little bit more formally now. If we set B, capital B, equal to mass, then we know that lowercase b is equal to 1, and we can rewrite the Reynolds transport theorem for mass as dm dt in the system is equal to d dt over the control volume of rho dv plus the integral over the control surface of the density times the velocity dotted with the normal vector integrated over that area. Now, for a control system, by definition, we're following a certain set of particles, and therefore the total mass in the control system is going to be equal to the change in mass over of the total system over time is going to be equal to 0, and we call that the conservation of mass. Now let's look at the second part of this equation. That is, let's look at the part of the equation where we're looking at the integral over the control surface. And if you remember, in the past we've talked about if we have a uniform flow with a uniform density, a uniform velocity, that we can write the mass flow over an area is equal to the density times that area times the velocity of the fluid crossing that area. Now, in a more general case, when the density is not constant or the velocity v is not constant, then this is generalized to the mass flow over a boundary is just equal to the integral over that boundary of rho v dotted with n hat dA. If it turns out that the density is constant across that cross section, then we can take the density outside, and we can define what we call the average velocity, which is just going to be equal to this integral over a of rho v dotted with n hat dA over the density times the area. If the velocity is constant across this area as well for uniform velocity, then of course the v just comes outside the integral once again, and we see that of course the average velocity is just equal to the uniform velocity v. Let's look at an example, and in this one we will look at the effects of, or how we deal with compressible flow as well. Let's say that we have a pipe, and we have some flow profile going into this pipe and some flow profile going out of this pipe. I've drawn them as parabolas. They don't have to be parabolas because we're just going to talk about the bulk mass flow in this case. And we're told that at section 1, the pressure is 100 psi absolute, and the temperature is 540 Rankine. Nice of them to convert to Rankine for us. And at the supposed to be a 2 at the outlet, or somewhere downstream in this pipe, the pressure has decreased substantially to 18.4 psi absolute. The temperature has gone up slightly. No, has gone down. Sorry, to 453 degrees Rankine, and the average velocity is 1,000 feet per second. And our job is to find the average velocity at the upstream portion of this particular section of pipe. So the first thing that we do is what we always do, which is we define ourselves a control volume, which I will draw in red here. And it will be the fluid inside the pipe, just inside the pipe, with the inlet being up here where at section 1 and the outlet being down here at section 2.